Hi everyone, it's Joshua, and welcome to my first ever video, which I'll be posting on YouTube. And what I'm going to discuss here, I'm going to discuss about um, a recent thing I did where I was working on a project, and that project inspired this blog post you're seeing on your screen. It talks about designing a local cloud for AI inference using Docker, Rust, and Python. And before I go forward, let me just talk about the project itself. So the project is it's meant to be interacted via add-ons from any of the popular email provider from Gmail to Outlook and what have you. Right now we have an MVP on Gmail. I think I have a sample here. I'm going to just show you how it works. Let's assume I have this Gmail here. It's a fisherman, and it reads your email and tells you it's spam on that. This one probably shows up my primary email, but it's actually spam. I don't have a sample to show you a spam email, but I have a demo page which I have on Vercel here that I could just test run it. This is a phishing email. When you analyze it, it reads it and tell you here's this phishing email and its confidence level and the rest. So that is pretty much what it does. So the idea is that I remember like years ago when I was at I think it was at Unbox. We had to do a bit of sessions called security sessions where we had to be trained on how to be able to detect emails that are phishing, that are fish or that can lead to leakage of like our internal data and the rest. So we had a lot of programs like that, including even them sending us some paid emails and some of those fields. So it costs money to hire people to teach us that. Also costs company time because we had to sacrifice like 2 hours or thereabouts for it. And if you fail, you do it again. Those things get smarter. Those people that send those emails get smarter over time. So it's hard to keep up. So why not have an AI model that could do that for you, and it's inbuilt into the app you're using, so you don't have to like copy the email and go to some apps to do it. It's just right there. So that was the whole idea behind it, and it was an interesting one because I had to do a lot of um, um, a lot of architecture around it, and I think I have the architecture here where um, it's a Mario page. Let me just open the different page so that we don't waste our time. But from here, let me just increase this a bit. The idea is that when an email comes into the email engine, when you click on this, an email listener, which triggers, which ideally, for example, now this is already open, and I come here, I probably open maybe Gray or something like that email. It automatically start. I don't need to click on it to start it. It automatically just starts on its own. So the idea, that's the idea here. That's on opening it, it triggers the whole process. In the background, I'm using Google Auth, so authentication is done. So when you send an email to the backend, I know you're coming from only the Gmail or whatever client we are using. Um, so that tracks also even getting the just the email of the person that's coming. So we're gonna have like a paywall behind it. Just add that there, and that's done for that. Um, so when it gets here, there's a backend side which is built in Rust. Then I also have an RPC agent here. So the idea is, which is what we have right now. I meant to update this um these drawings. Before it leaves these Gmail clients, there's an encryption done here. So your email is encrypted here, so that while it goes through all this setup, it's just gibberish, and so they decrypted in this RPC agent that has an interaction with the LLM, the inference, which is directly. So it's decrypted there before then sent to the LLM. So that is where the whole magic comes. So because we realize that emails are very sensitive and they are private, it has to be handled with much care. And so that even if during transportation it gets intercepted, you can't the attacker can't even access the data. So that's the whole idea. So when it gets here, it gives the response. It's consumed there. The data is not stored anywhere. No retention of data is happening. Then once that is done, it gives a response to the backend that hey, this is the whole data. Then it responds back to the acceptance UI, which is the UI there. And then we have an agent that then if it's a phishing email, it then triggers, hey, do you mind if I push this to delete it or send it to spam? It's your choice. And that is the basic architecture of the whole program. So that being said, so the whole idea is that when you build such a program, you need to, because when you're interacting with um, the Google runtime, because the add-on part is actually hosted on Google runtime, so you need to at least have a URL to pass there. Because if it was just like this, for example, I'm doing this, I could just put in my localhost, blah blah, and it just runs it directly. Fine. But when you're dealing with Gmail add-ons, you need to have a URL, like a platform URL API endpoint, to pass to this thing to Gmail to be to access it because you can't understand localhost. That's why it's necessary for you to have that. So I thought about it that instead of having that kind of thing, and it's gonna cost money. Although I know it does offers some free credits for a start, but why should I go through with that? I mean, why should I bond that free credits right now? Plus, yeah, I just thought, why not do something fun? So that's why I decided to build my local insurance, which will mimic ECS and also optionally having to use Lambda in case of maybe want to like have a Python script, which we won't be using, but in just in case. So back to the blog post. We talked about how we get talking about all these parts, and so basically, excuse me, when we talk about an AI system generally, it's always covers basically three things. The UI, which for example in this context we're using Gmail add-on, so no need for that. We have to at least design it a bit. So this is not like the best, but it get better. Um, you have the UI, you have the backend server which takes in the direct call from wherever the UI is to the backend, and the backend could do so many things. Then you have the LLM itself, which we run on an LLM inference engine. I know if you're running on AWS, you can use Bedrock. If you're using the popular ones, the frontier models, or if you have your own custom model, which in this project I had to build, I mean, I had to work on a custom model for it. So because initially I started it, I used, I think it was Llama I used. It was, the inference time was a bit slower, but getting like, to get a response, get like a 1 second to get a response. So, I mean, that's really the best. Most times it go like 2 to 3 seconds to get a response, which wasn't really the best. Um, so for Llama 3.2, it was a hit or miss. It was sometimes it worked, sometimes it doesn't work. But it was fast. Then when I started to use like a higher model like the I think GPT-5, it was slow, but it was always accurate. So why not just have your own custom model, very lightweight that could go very fast? So that was the idea. At some points, when I was testing locally my GPU, I was getting response as fast as like 170 milliseconds. It's very impressive for like another of them. So that being said, so let's talk about now the local cloud provider. Um, so like I said, I built the backend, which as you can see here in Rust. Um, and for the backend server, we had a in the backend server we had, like I said, it only just handles requests. When it comes, it then directs to the RPC call. So it makes an RPC call to this the RPC's agents, and because so we don't like cost so much because like I mean I had a lot of like add another cost on like the timing. RPC was a very good deal because I mean the type system already takes it's faster anyway. I don't want to go into the details on TRPC. You could just Google about it. It's still the same as it's the same technology behind gRPC. The RPC model, I mean protocol itself. That's what actually handles the computer of them. TRPC is the one custom bit for Rust. It just so then you're writing the your protobuf schemas. The TRPC just focuses on using the Rust type system to handle that part of it. So the backend server is made. Once it gets the request, it just reroutes it to the RPC server and so on. So it has very light. It's pretty much like a wrapper around the RPC server, RPC agent, which is this. So now in the RPC agent, there's something interesting that happens when you're using a local inference, which is what I'm using because the model is running right on my laptop right now. Um, I'm using because I for now I haven't really gone deep into like looking at libraries in Rust that can do inference, but from what I've researched so far, it's not that much. So I decided to just go with just using Python to write it. So that's why most of my the RPC agents basically just use Python mostly. This is no, not this. RPC spam creator server. So this RPC server basically just that handles the main thing. So what it does is that it gets the details and then calls the RPC server. I'm using a library called PY03 and it's fantastic. So literally, I could just it's kind of similar to where you have the FFIs where you can call C++ in this thing, but um, this is way more easier than that. So you don't need to have like a build runtime. I think it does it for you. I haven't gone deep into reading into like the library, but that's what it basically does. So you could literally call a a a Python code inside it, and this is a snippet of a code here. So when in the RPC calls an invoke function, what it does is that it calls this Python the py3 and it calls a script name and the particular function is going to call. Let me see if let me pull up an example of the code itself. I think I have it here. So we have to do some caching because for a start it needs to have like a cold start similar to how you have like a lambda kind of thing where you have a cold start so it warms up and it's up and ready. So we have that kind of thing here. So we have the caching, but here is the main function it calls a predict function. So the predict function basically just takes an input and calls out our model here. It tokenizes it, then it calls the model. And let me show you. As you can see here, it's calling the cache model and it gives a response. Then we mark it because it's not. I used this Microsoft Alberta model, so it's not like the typical model that you just pass some data. I mean, your data, the system prompt, and the rest. This one doesn't work that way. I could go deep into that, but that'll be a whole lot of that's out of the scope of this discussion. So here, so we call this function this local inference, and we call the particular function here, and we're able to get our label as call, and that's what we respond to. So okay, I think I even had a snippet of it here. So what does that imply? Now, sometimes you think about the cost of having to call this, and I actually checked the logs because I did a lot of tracing, especially telemetry in this whole system, and the costs of the overhead of this is very very lightweight, very 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 little. the major cost we have is just the input. Compared to the initial, the only time it takes longer time is the first call, um, which is already which is not much now because I've done the first. I, I, I I should have pulled up at the signals dashboard, but I'm not starting right now, so that will take a lot of time. But anyway, um, so yeah, we're able to call the function here, and once the function gets our results, we're able to map it into our struct, which handles everything, which handles the whole response, and we're able to like return it to a JSON and respond it back to the API, and that's what you get, which is what I mentioned here. Okay, I also mentioned how you need to initiate the model once, so it's reused. If you don't do this, for every call you are doing, it's restarting the model and making a call, which will take so much time. For context, a typical one takes about like 300 milliseconds to like restart. So if you just start for the first time, you probably get like the first call will probably take like about 700 milliseconds. Then subsequent one will be like 200 to 800. That's like the average um, response. So now the orchestrator, ideally, and this is where Docker comes in. So I mean, if you're using um, ECS, for example, on AWS, you pass in your Docker image. You pass the Docker stream, your code will be there, then you have it, your Docker image, which you probably link to your GitHub repository. So you have some CI/CD that triggers it. Excuse me. You have some CI/CD that triggers it. So when it triggers it, when you make a push, for example, to your GitHub, it triggers a new Docker build on your on AWS. You can also use DigitalOcean. So I remember using it for a project some time ago. So for every push to the main, so I for the best way to handle this is you have the staging branch, you have the main branch. So staging is when you like test run things. Then when you push the main, that is the main thing. So that one triggers a Docker build on whatever cloud platform you're using. For AWS is the AWS cloud, I mean the ECS. For DigitalOcean, for example, it's just the I think it's the app platform. I can't remember. It's been a while since I worked on that part. So once that is built, um, it is running. So for the context of these projects, like I said, we have like multiple servers. So we have this server and this server. So we have like two different servers. For having those kind of things in in the cloud setup, for example, you're using AWS right now, you need to find a way of communicating within two of them. And if you're using AWS, communicating two of them is very easy because I mean you're under the same accounts. So you probably need to have some form of role to be able to call different component. I mean Docker images in this context. In it. In this way, there's no storage, so you don't really care about that. So the main thing you're caring about is how they can communicate to each other via APIs anyway. So that being said, um, so like okay, I mentioned about how GitHub Actions helps you trigger the Docker building, which I said was also being hosted in, for example, ECS, ECR. I've mentioned ECS as well. AWS ECR, because they're the same cloud, so you don't need the same. But in our context, we're using Docker Compose in our context. And a typical, for example, we're using here, we have in this. So we have our two services. We have the add-on services, and we have an RPC client here. Um, so for here we have our Docker file, which each folder has a Docker file, as you can see here. And for this one, you also have your Docker file here. And there's also env file for each one, but no, we're using a general env file, which I don't want to open because I have some secrets there. Then you have some specific environment that can be gotten from it. In the context of when you're using AWS, you could have a Terraform that extract that data from your GitHub action. I mean your GitHub variables, secret variables. So that could be done, but this also like is also doing the same job. If I use this one to deploy, it will also get that same data from my GitHub actions. I mean my GitHub variables on the repository. So then you deploy for the resources here. It could vary, but all these things could be set inside AWS or if you use DigitalOcean. It doesn't matter which one. Then the same thing, you choose you have to choose the specific ones you need for each and every one of them. The same to the RPC, you choose the type of data you want, the type of environmental variables you want. For example, I was in this because I was in the local. I probably don't need this anymore. Let me just delete this. That was when I started initially. I was trying to like use an Olama data for it. So, so in context of this, now it does region as its key. Those things can be gotten from your env. The pi3, this is for the file name, which doesn't really need to be there, but I mean, I just wanted to, I used it to create the configuration file. That's why it's here. So it's not necessarily a secret, but it's just there. Then the port and the log are all there. These are not necessarily secrets compared to the first three ones. Then this is if it's a production dev environment or local environment. Then you can choose your deployment stage. Then you can also set up your network here. This is not necessary here because I realized that setting up network can be a bit annoying. It works, but it's oh sorry, I'm just checking. So if I set up my signals, for example, on Docker, I deleted the image a couple of weeks ago, so restarting will just be annoying. But that being said, if I have my signals running, I'll just turn this on. If not, it just be showing up errors and not let my Docker compose run. So that's why it's commented out. So yeah, those are like the basics of how this is running. So the endpoint of this signals net URL endpoint is what we pointed here. This OTP collector endpoint. That's what we're using here. So yeah, I wish I could show you my env, but in the env file, you could find the URL, the endpoint of these signals here. So it won't be like typical where you have localhost, because it's run on Docker, so it would be like signals.net column, then the endpoints kind of thing. So yeah, so this basically just give us our form of CI/CD deployment feature. So that means on just one command, I could just shut down my program and restart it. So that will probably be something like this: Docker compose build, and you're going to shut it down. Just Docker shut it down, and it's very fast. So it just stops your container and starts it. I could bring it up again and just do Docker compose up. Sorry, build, and it restarts. You have just do Docker up and it just runs, but yeah. But the good thing is that it's be fast because a lot of things have been cached already, so it's not much of a big deal. I think the only part that will probably take a longer time is because most times it rebuilds my the Rust repositories. And the funny thing is, I mean, we all know how Rust build time can take a long time, but before you know it's done, my sense is being fast, so it doesn't really cost that much. Yeah, and so far we've talked about. So now for a typical cloud deployment, you talk about the main your build on the cloud. We talk about like ECR, where you host your container on the cloud. Once that is done, you have now you have the two clouds, the two containers running, and it's communicate to each other because one of the cloud depends on one of the cloud, one of the image depends on the other one, which is the RPC server. So we could have both of them running the same cloud, and they have to communicate to each other, which would be easier if you're in the same cloud. Like for example, it's AWS or it's Docker. Either one, you can easily connect both of them together. It's very seamless. Once you're on the same account, anyway, it's easier. So one of those two is to how you now expose that to the cloud in the context of if you're using a local cloud. I got to know about Ngrok, and it's fantastic. It's able to give us that power to have that running. Um, the main server that we exposed is running on localhost 8080. So once I run Ngrok, this command, it just runs. I have it run already. That's why it's working, and you could even see traces of every response working. Every response. So we have the analyze, which is the main endpoints for the one from Gmail. As you can see, it shows a 200 here, and the one for the demo, okay, which is this, it's showing here. So yeah, that is, so with that we have our URL here. So this is what you just pass. It shows, and this is the way you forward everything. So it's forwarded to this URL. So this URL, once I put this URL on mine, it's redirecting to my local host running on 8080, and that is it. So yeah, that is the beauty of it. And with that, I can run right now. It's, let me see if it's done running. Not yet, but it's still running. When it's done, I'll restart this, and I can still run this, and it will work. And that's what I've been using. As you can see here, we can see the logs from Ngrok here showing that yes, it got the responses from this, and it works. So that funny thing I also added is, now please don't bombard this URL because it's going direct to my laptop, so it might bombard this and it might crash. But the funny thing is that even if you do, it won't crash. So let's say, for example, I do, or I need to run finish. Let me show you something cool. Because I thought about it that, yeah, if someone lay hands on this URL, it might be a big deal and might crash my laptop. So there is a rate limiter on the URL, especially when you're coming from these endpoints, the analyzed endpoint. Because for this, you can't really reach out to this endpoint without a Google authentication, which that means you have to come from your email. So that means you should be ready to open like thousands of emails to crash. Well, it won't crash my listing, but I'm just saying it will take a long time for that to have any effect on my laptop. So the only way you can probably just crash my system is probably go through this demo analyze, and for that there is a rate limiter. To say you could test run it, you could try it out, but there's a rate limiter for it. And yeah, so that is the cool thing about what I did, and it's just fun. So if you have time, you could read this blog post. I will also drop you in the link to this bio, to this video, and let me know your thoughts about it. Thank you, and I hope you guys enjoyed it. I should do more of this. I really enjoyed myself. Anyway, have a good one, everyone. Bye.